My name is Borja Arroyo. I come from the University of Cantabria in Spain, and together with the authors included in this slide, I will present the work entitled Application of the Incremental Step Loading Technique to Small Punch Tests on S420 Steel in Acid Environments. The exposition will be developed in the points included in this slide. We'll start with an introduction, material environment, we'll explain the experimental methodology, the results, and finally a conclusion about the work. Energetic industry, as oil and gas or offshore facilities, have used during the last decades high-strength steels in order to fit their requirements. But these materials combined with the environment in these situations and the protection systems employed can lead to stress corrosion cracking or hydrogen embrittlement issues, which can lead to subcritical failures. So these materials in this environment should be studied. In order to do that, standards such as the ISO 7539 or the ASTM E1681 have been developed. And among the tests included, the slow stern rate tests are the most commonly used. But these tests basically consist on subjecting a sample to a certain load in the environment and waiting time until failure take a lot of time and a lot of samples. In order to try to solve this issue, the standard ASTM F1624 has been developed, which can give a threshold result in a time of around a week using at least 3 samples. But there are cases or situations in where standard tests cannot be performed due to the impossibility to obtain samples according to the dimensions imposed by these standards. In these cases, the miniature test family and mainly the small punch test that we will study in this presentation, in this work, is one of the most commonly used to solve this issue. This test, the small punch test, has a European standard draft since 2018 that will be a draft probably this year, and it was validated to be used for characterizations in aggressive environments. So the objective of this work is to study the suitability of the ASTM F1624 step technique to be applied to the small punch test, proposing modifications and adjustments necessary to implement this methodology in this test. The material used for our research was a thermomechanically treated 420 steel or S420, which is currently used to build offshore components and pressure vessels. The mechanical properties and the composition of the steel are shown in the tables included in the slide. The environment applied was a cathodic polarization, also known as cathodic charge, which basically consists of interconnecting the steel to a nanode of pure material, which in this case was platinum, imposing a constant current density between them. The electrolyte employed was basically a 1 normal dissolution of sulfuric acid in water and 3 levels of intensity of 1, 5, and 10 milliamperes per square centimeter of submerged sample were applied, which are in fact 3 different environments. To understand the methodology that will be proposed, first of all we need to explain what the standard ASTM F1624 is about. It basically consists on applying a sequence of steps, which is called the step profile, on a sample introduced inside the environment. A total of 20 steps in each step profile are always applied, but the duration of these steps is defined in function of the hardness of the material. So first of all, we need to perform a hardness test in order to know the hardness of our material. If it is lower than 33 Rowell C, the methodology, the step methodology cannot be applied. If it's in between 33 and 45, we will apply 20 steps of 5% of a maximum load that will be defined later, with a duration of 2 hours the 10 first step and 4 hours the second 10 steps. If the hardness is in between 45 and 54 Rowell C, the step duration will be 1 hour for the first 10 steps and 2 hours for the rest. And if the material is very hard, so harder than 54 Rowell C, the 20 steps of 5% of that maximum load each one will be of 1 hour. That maximum load that we have just mentioned is obtained from the maximum load of our material in a tensile test performed in air, so a regular tensile test. So the first two things that we'll have to do prior to applying the step methodology is performing a hardness test in order to know the step profile, and then performing a tensile test in order to obtain our maximum load to start, which is called PFFS, fast fracture load. Once this is done, the first step profile is started. We take that fast fracture load, we divide it into 20 steps of 5% each, and we start doing these steps until the specimen breaks. In that case, we will obtain the threshold load from the first step, which is called PCH1. This value is incremented by 10%, and that is divided into 20 steps, and we perform the second profile until the specimen breaks, and we obtain the threshold load from the second step profile. Again, we increment the load in 10%, we do the third profile until the specimen breaks, and we obtain a third threshold. And we continue doing that until we reach to two thresholds which difference is lower than 5%. And that final threshold is the threshold load that is obtained by applying this step loading technique methodology from ASTM 1624. So at that point, the methodology that we have applied in our work in order to characterize our material in the environment following the standard is just doing that. We had and still having 35 Rowell C, so we applied a step profile of the 10 first step lasting 2 hours and the 10 second steps lasting 4 hours, which were applied after doing a pre-charge of the material during 24 hours in the environment, which is necessary to be done. Prior to explaining our proposal, we will explain how the small bench test under constant load is performed. The samples used were in accordance to the standard draft and had 0.5 millimeters of thickness and a square section of 10 by 10 millimeters. Then the sample is introduced in between two rigid clamps inside the environment as shown in the figure and in the schematic. And then load is applied on the top of the punch, which is then transmitted to the sample. So our proposal for the step loading technique application to a small punch test is basically changing those aspects that are more convenient for the architecture of this test. First of all, we obtain the fast fracture load by performing a small punch test in air at regular rates following the recommendation of the European Standard Draft. Then, for our 35 Rockwell C material, we need to do 20 steps of 5% of this value each with a certain duration. In our case, instead of 2 and 4 hours for the 10 first and 10 second steps marked by this standard, we choose modification of this duration that will be 20 and 40 minutes. Why? Because as the specimen is much thinner, we have proposed that the time must be much less. And as we needed to start by trying some time, it was convenient 20 and 40 minutes because the 20 steps will be 600 minutes, which is a total of 10 hours. So a test could be performed in a day, in a working day. First, prior to the mechanical testing, a pre-charge in the environment of 2 hours is proposed instead of 24 hours. Because of the specimen thickness, this time is used in the lecture. So now we arrive at the results. On the left, we can see the results of applying the standard ASTM F1624 to the 3 environments studied of 1, 5, and 10 milliamperes per square centimeter of submerged sample. And on the right, we can see the same thing applying the small punch test proposal to the same 3 environments. At the first sight, we can see that the step profile and duration seems to be more or less consistent and following the same trend in both cases. If we calculate the threshold stresses for the standard tests and the threshold loads for the small punch test proposal, and we put them face to face in the graph, we can see that in both cases are following numerically that trend that was told about in the prior slide. Even for the 10 milliampere per square centimeter environment in which the material was saturated, well, in fact it was close to saturation at 5 milliamperes per square centimeter. This trend was shown in a similar way in both cases. So, as a conclusion, we can state that the proposal for the small punch test threshold load of tension based on the ASTM F1624 methodology was validated, proving that it was valid for the S420 steel studied in the 3 different environments employed. The results should be extended to a wider range of materials and environments as a future work and studies about the small punch steps durations should be deeply performed. Just before finishing, uh, the authors want to thank the University of Cantabria for the finance to perform this work. Thank you very much for your attention.